My name is Pat Schoen, and I'm going to be talking about knowledge for induction of Arabic morphology for the next 10 minutes that I have. You may be wondering, why am I interested in inducing Arabic morphology? Well, for one reason, it has never been done before, to my knowledge. But the more important reason is, if it can be done, that we can induce morphology, and if it has value to language modeling, then we can do it across a wide spectrum of languages without ever needing an expert to provide us the morphology in those languages. So how might we go about doing this? Well, Dan Jurafsky and I a few years ago were working on an algorithm for inducing morphologies of languages that had a significant number of inflections in particular. We were interested in generating words that could go into electronic dictionaries, so we were paying attention to words that occurred 10 times or more. The way we processed words was initially to look for words, place words into a character tree or a trie, and look for common beginnings and endings to those words, such as car and car, car and cares, car and caring. Then we use latent semantic analysis as a process of inducing semantics on each of these words and trying to see if semantically they are paired up. Those words that are paired up semantically were then kept and determined these are valid morphological relationships. Those that were not had other processes that went on to them, such as looking at the frequency information that's contained therein, the local context, or looking at weak transitivity relationships. The problem with using a trie-based algorithm, a character tree, to do Arabic is, in addition to having a significant number of affixes like these inflectional languages, they also have these templates that was talked about earlier. So for example, here's a word, and there are 4 words that it's related to morphologically, and all of them have a $sign, a G, and an L. But as you can see, the $sign, G, and L do not necessarily have to be contiguous, as you would expect in an inflectional kind of language. So that means we need to expand on the process of doing this trie-based algorithm. I should mention also that because of these templates, as well as the affixes, there are 3,576 words in Call Home Alone that had over 50 things that they were related to. So one of the ways that I thought about for trying to find things that might be morphologically related to start is by using minimum edit distance. So here, for example, I can take this word and say, I want to go try to find things that might look like that. I can use minimum edit distance on all the words in the dictionary to find, say, the top 100 or 1,000 that might look like it. Unfortunately, there's lots of words in the dictionary, and minimum edit distance is not a slow process, so I need to speed this up. So I used an information retrieval-based approach to facilitate this search. Basically, I treated each of these words as if they were like a document, and each of the characters or the bigrams or the skip bigrams or whatever as if they were the terms of the document. And then I would use that word as an exemplar document and say, go find other documents that look like this one. In other words, go find other words that look like this word. So this was the first expansion on the other algorithm, using minimum edit distance instead of character trees. The second expansion was to improve the ability of looking at words based upon frequency information. So in this list, I did 2 lists here. These I'm going to call rules. These I'm going to call stems. Rules basically are items that show up in your dictionary of things where like I can have a word X and a word ill plus X. I can have a word Y and I can have a Y followed by U. These things show up 1,178 times in the dictionary, 635 times, and so forth. I can also look at the things that could fill in the star positions, and these represent the stems. So Gaia, for example, shows up 507 times, and so forth. Previously, when I looked at other languages, if the frequency or if the stem count was high, that represented something that was probably less likely to be a valid relationship. But in Arabic, these things you see here on the top are typically valid relationships. So what I did is I threw away the frequency processing I was doing before and thought, let's just do it based upon bottom-up clustering. We'll take 2 words and we will treat the weight between those words based upon the count of the times I saw the rule that mapped me from one word to the other and the square root of the paired stem observance. So this is the second alteration to our original algorithm. And the third is an update on the way we did transitivity. So suppose I have 2 words, X and Y, and I know that X, based upon semantics, is morphologically related to Y. And suppose I also know that Y is morphologically related to Z. But I do not know that X is related to Z, and I want to try to induce that relationship. What I can do then is to I made this transitive relationship, or something akin to transitivity. I said if x has been shown to be related to y, and y has been shown to be related to z. And then if I look at the intersection of characters between x and y, and that's reasonably large, say 3 or more, and if that intersection also exists within z, then I will say x is related to z. Now, when I was doing transitivity processing before, transitive would give me like 0.1, 0.2% gains. This is giving me about 1.5% reduction in error. So you might say, what do you mean by reduction in error? Well, I guess I need to talk about how do we score morphology. So we score morphology based upon conflation sets. A conflation set for a word W is the set of all words that are morphologically related to W. So we saw this example before, that this word is related to these 4. So suppose I choose, I call x of W the induced conflation set for W, and I let y of W be the one that I derive from the call-home lexicon. Given this information, I can compute the number of things I got correct, the number of assertions I have, and the number of deletions I have by looking at these set relationships. And that, of course, allows me to compute error. So over the course of these 6 weeks, I ran a number of experiments, and I obviously don't have time to discuss them all. So I'm going to say, initially, the algorithm was looking at these kinds of things, suffix and prefix kinds of things in other languages. But when you started looking at, and things that occurred 10 times or more. But when you looked at affixing and symplectic morphology, it was not doing very well. These are error rates, 39% error. After the 6 weeks were up, we had improved the symplectic morphology by the overall morphology by 5.4%, and suffixes and prefixes by 3% each. But language modeling is more interested in all of the words, because the low frequency words are the ones we don't have enough information about, and we would like to know more. The algorithm, when we first got started, was not doing very well, only 27.5% on suffix and so forth, and only 57.6% on general morphology. And after the course of the workshop, I was able to get these two down by 4% and this down by 5%. So there's still a lot of room to go down here, and a lot of them have to do with the fact that these very long conflation sets. There were 2,800 of them that had more than 100 things in them. But nonetheless, I thought it's a good time now to use morphology that's been used to try to do language model rescoring. So there's a number of things one can extract from a conflation set. One can extract a stem. I'm declaring a stem of word W to be the smallest word Z in W's conflation set, where Z is contained in W. I call a root the character intersection of all the words in the conflation set. And the rules, patterns, and classes are maps between words and stems and roots, and words and roots. Now, I didn't run language modeling rescoring on all of these. I ran it on those that expert knowledge seemed shown to be pretty good. So one of those is the root. So I used the VBN language model and the one that Catherine and Dimitri had to build, which had this baseline error rate. And I added root information to it, and that only gave me a 0.2% gain. When I used the other pieces of information that were induced, I didn't get really much of any gain. Even here, you see, I coupled roots and classes, and that did not give me any improvement. So I went and I said, well, what happens if I had done roots based upon actually the conflation sets that I'm getting from the call-home lexicon? And it gives me, at best, 54.2% on the root. So I'm pretty much getting as much as I can from the equivalent to what the call-home lexicon would give me. There is more information I realized last night that I could be deriving from class, so that's where I'm going to be working on next. The last piece of information I want to talk about, I was going to ditch this slide, but since it came up earlier, it's about using morphology to induce words that were previously out of vocabulary. So because of the fact that I've induced all these rules and stems and information, I have the ability to propose words that had never been seen before. And so if I use just the rules that I've seen and try to propose extra words, I proposed 1 million words that had 41.3% coverage. So that would have reduced the out of vocabulary from 10 to 5.9%. Likewise, it can be a little bit more constrained when I generate the words, and I can actually have produced a set that had 100,000 words and gave me 25% coverage, so it would reduce it from 10 to 7.5. We didn't have time to experiment with this in the recognizer, but this certainly is a direction that we could head. I'm out of time. Does anyone have any questions? Good. Okay, thanks.
Pat, Andre, okay.
Oh, yeah.
So I just learned from in the hallway that these vowels in the patterns, they actually can occur only in those positions. They can't occur anywhere else. Is that correct?
I don't know. My program did not know anything about extra. It was basically completely blind.
If that were true, then couldn't you just strip those vowels and basically apply your concatenative algorithms just by rearranging the way that the characters are ordered and turn it into a concatenative algorithm?
Maybe, but I actually tried this algorithm on the script form, and actually performance went down by 5%. So and the script form, the vowels wouldn't be there. So I'm not sure.
No, you would keep the vowels, but you would put them like after the root.
Oh, I see what you're saying.
Yeah.
Yeah. So there might be other things that could be done here.
Good afternoon. So in the following 10 to 15 minutes, I'll be presenting work on text selection, both done by me and by people at the BBN. So the motivation for doing text selection, I mean to select text from available text data, from select segments that are conversational in nature. So hopefully we can add those selected texts to our training data to build better language models. And that's the motivation for doing this. And given this task, the approach I used in this workshop is to use part-of-speech-based language models because part-of-speech-based language models have been shown in the past to better indicate language style differences rather than like vocabulary differences. And here are the steps I followed. First, I trained a part-of-speech tagger on the available data we have. Then I trained part-of-speech language models on formal and conversational text. So we have two language models. And I tagged new data on which we're hoping to do text selection from, and select segments from the tagged new data, and and added those to our training language model. The data we have three sets of data. We have the Arabic tree bank, which is 130,000 words of tagged newspaper articles. So this is formal Arabic. And we also have Arabic call which is transcribed phone conversations. So that means it's conversational. So we use these two data sets to build the tagger and to train the two language models. And the Al-Jazeera is the data on which we'll be doing our text selection. It's 9 million words of transcribed TV broadcasts. It's mostly news, which means it's mostly formal, modern standard Arabic. But it's hoped that it also has some talk shows and interviews which will be more conversational in nature. Here's the implementation of the tagger. It's a standard Viper model. What it does is finds the most likely sequence of tags given the sequence of words. One word about the unknown words. When tagging new data, you're going to come across unknown words. And the assumption here is that unknown words is going to behave like singletons, which are words that only appear once in training. And I doubled the data, and in the second copy of the training data, I replaced all singletons by a special unknown token. So in this way, half the probability mass of the singletons is assigned to the unknown words. And the tools I use is GMTK, which is a toolkit developed for training graphical models and using graphical models for decoding. And the training is standard EM training, decoding is perturbing. So there are several experiments. First, I ran an experiment on the English pen tree bank just to get an idea if this approach actually works. And it did. So I moved on to Arabic. I ran experiments on tree bank and tree bank alone and both tree bank and call home with supervised and unsupervised training. And here are the results. The baseline are obtained by assigning each word the most likely tag it can have based on different levels of knowledge we have about the language. Except for English, where 79% is obtained by assigning each word the least likely tag we have. 95.5% is the most likely tagger. for each word. So so we expected our performance to fall somewhere between there, and it did. So after building the tagger, after having built the tagger, I used existing scripts to build the two language models. Call home, which gives the conversational language model, and tree bank, which gives the formal language model. And these are all part speech-based language models. And text, and I assign a score to each sentence from Al using the log likelihood ratio. So this score, basically a score of greater than 0 means that particular sentence is more likely to be conversational than formal. And here is the score distribution. So the red line is call home distribution, and the blue line is tree bank, the green is Al Jazeera. On this graph, the vertical axis is percentage. So you can see call home and tree bank has very different distributions. And the Al Jazeera looks very much like call home, or very much like tree bank, except it's got a tiny tail that extends, that the portion of it that looks like typical call home sentences. So it's this part that we're hoping to extract from Al Jazeera and add to our training data. This is shown more clearly on this graph, where the y-axis is the log count of sentences from three data sets. So here we can see that there are like thousands of sentences from Al Jazeera that look pretty conversational in nature. And we've got these sentences, and they're about 150,000 words, and it's about the same size as call home. And we added it to the training data for our language model. But unfortunately, there is no reduction in perplexity. The possible reasons for that is that either there's just no conversational data in Al Jazeera, or the data they have is very different in style. And also I'll be presenting text selection work done at BBN. This is done by Rich Schwartz, Mohammed Nomanay, Daniel Liu, and Nikolai Duta. So they first tried to search for dialectal text, which is conversational text, both on the internet and on broadcast news. They used unique word, the keywords search, words that are unique to conversational Arabic. But on the internet, they didn't find a lot of data. And when they search it on broadcast news, there's not a lot of data, and the typical occurrence that they found is when the speaker uttered one word in conversational Arabic, but then switched back to modern standard Arabic. And that is not good data for training language models. And they tried, and they also tried several ideas where they tried to combine modern standard Arabic with call home. So the first idea that was tried was to combine language models from modern standard Arabic or call home and assign different weights to them. So interpolate the two language models together. They used SRE toolkit to find the optimum weight for the two language models. But there's insignificant reduction in perplexity. Then another idea that was tried was to use classes. The idea is that two languages might be very different, but they probably have the same classes. So they used the SRI toolkit to derive the classes, then they used call home data to find the n-gram n-grams of classes, and the probability of a word given a particular class. Then combine this resulting new model with call home word trigram. But result is still no gain. The last idea that was tried was to still combine the two language models from modern standard Arabic and call home, but only make changes when the change are likely to arise because of insufficient training data in call home. And here's how they do this. So for a particular n-gram count, if the difference in call home and modern standard Arabic, the n-gram count in those two language models is more than the square root of the length of their n-gram, then this is a change that we don't want to make, because this is more likely to due to differences in the two languages rather than just having insufficient amount of training data at home. So they did this, but still there's no gain in the resulting model. And that's the end of the presentation.
Okay, now we're going to have the two graduate student proposals. The first speaker is going to be
Good afternoon. My name is Gang. Here I'm going to give a proposal on learning and using factor language models, which hopefully will be extension of the workshop. First of all, I want to just warm up a little bit, talk a little review about factor language models. And as a proposal, I'm going to talk about how we can find the structures in the factor language model. And once we found them, how do we use them in the first pass decoding? The idea behind factor language model is, aside with words, we might have some other factors such as stems, verbs in Arabic that are quite useful in building the language models. And factor language models can also provide new possibilities for designing those language models, such as Jeff talked about multiple backup paths, different smoothing techniques, and so on. But we have a problem, because in the factor language model, we have different factors, we have the different time frames, so we have a whole set of choices that we can make, and we don't know what to do. There are a couple of solutions. We can do it by hand, using some expert linguistic knowledge to build up this factor is related to that factor, so on and so forth. Or we can use pure data-driven approach, and the data help us to make the decisions. Or we can combine these two techniques together. Here I propose a solution which is, I call it evolution-inspired search, which is directly related to the genetic algorithm. And the key idea is the survival of the fittest. Suppose we have a set of possible factor language models. Here each node represents some specific factor language models. And some of them are good, such as the green ones. Some of them are not so good, such as the red ones. So in the selection part, one keep those good ones and remove all the bad ones. In the next part, we want to get some new factor language models with those good ones that existed. And we're trying to combine them in a way that we can retain the useful characteristics to get at some new language models. After that, we might want to tune those language models a little bit. I will talk about that later. And get a whole set of new language models so that the overall performance would be better than the first generation. There are a couple of advantages to this. First, this can find some good models quite quickly. And the reason is, in each step, we're trying to maintain all the good part of the previous generation. And the other good advantage about this is this can be run in parallel. Because for a set of language models, we can train them and score them individually. And this process can be implemented in parallel. Well, what do I mean by good language models? And then the quality, we can have several ways to define them. We can just use the perplexity on some development set, or we can rescore on the development set. Another approach would be use complexity penalized perplexity. The idea is trying to avoid the overfitting issue. As I mentioned before, there are 3 steps in the algorithm. The first part is selection. I already implemented the so-called stochastic universal sampling. The idea here is for each language model, they have a probability to survive. And the probability would be proportional to the fitness. And those fitness is directly related to the quantity that I described before, such as word error rate or perplexity. And the next step is combination and mutation. In a combination, this is important because we want to maintain the good features of the previous generation. Here, we have several strategies such as inherit structure horizontally or vertically. I will talk about that in detail. In the mutation part, we can just, for some language model, we can just add or remove some edges, or we can change the backup strategies or smoothing methods. This slide shows how do we get from one generation to another inheritance. So this will show you inheritance vertically. I'm more specific. I'm looking at this node, the possible parents for this node. What I did is, for some language model, I look at one frame, and I will try to inherit all the features of that frame. And for some other language model, I look at another frame, and I inherit all the structures in that frame. And I keep doing this until I get the whole model. Another approach would be quite similar, but just vertically. The idea is instead of trying to maintain the structure in a frame, here I'm trying to maintain the structure according to factors. Now, suppose we already have the factor language model. How do we use them in the first pass decoding? Well, why do we want to do in the first pass decoding? The reason is it might be very difficult to just do rescoring. Yeah, we might have more gains if we put the new build language models just in the first pass decoding. And we can do this. We can do this, but we have some trouble because most of the existing tools, such as HTK, they handle HMMs, but for factor language models, this is kind of general graphical model. But hopefully, we have a very powerful tool developed last year's workshop called Graphical Model Toolkit, which can handle all kinds of direct graphical models. And next, I will show, to speed up the inference, we will use a brand new notion about which we call it graphical model space lattices. So this slide shows the factor language model shown viewed as a graphical model. So if we add acoustic to it in the first pass decoding, we just hook up the graphical models for acoustic part, combine them together, and put it into GMTK so we can do training and decoding. But we have a problem because the decoding might be very expensive because we have a very complex model. The idea here is, in the first pass, we will use some simplified model, and that simplified model will do a first pass decoding and output some kind of lattices, or talk about what I mean by these lattices, because this is new. And after that, we can use some more complicated model and do a second pass just based on the lattices that generate on the first one. Okay, so what I mean by the graphical lattices. In the word lattice, in a general sense, which is based on the Markov chain. So the first graph is the graphical model Markov chain, and the second part is the lattices or state transitions. So in here, you can see that for each edge, for the edge in the Markov chain, because it only has one parent, there is a probability associated with the arcs in the lattice. So each arc in the lattice, there is a score or probability associated with it. But this got more complicated if you have a very general graph. So the top one is one kind of general graph. These nodes can be any kind of hidden nodes in the graphical models. And you can produce some state transitions. But if you look at this node, this one, it has two parents. So in this case, the arcs in the lattice, they no longer have a score associated with it. Instead, the combination of those two will have a score. Therefore, we need a brand new data structure to store this kind of lattice. Since I hope this will be an extension of the workshop, I will continue to use Arabic Qualcomm data, and we have some existing tools. For the tools for evolution inspired search, I already included most part, except that in a mutation we need to add smoothings and backup paths part of it. For training and rescoring factor language models, Jeff already modified the SRI toolkit, which can do that. And in the multipath decoding, we already have the existing GMTK. We only need to add more features such as output graphical lattices to them. And that's it. Thank you.
The last presentation for today is going to be by Shory Glass, and it's his MSU.
Good afternoon, I am Shory Glass. Today I am going to present a proposal regarding adaptation of modern standard Arabic-based language model to Egyptian Arabic. Now, as stated earlier by the previous speaker, that Qualcomm data is too less to build an adequate language model, whereas the modern standard Arabic we have lots of data. But it has already been pointed that there exists considerable difference between the two language models, between the two languages, and hence the simple interpolation or merging of the data won't help in building a good language model. Our model should have certain constraints. Our model should be such that whenever there is a difference in estimate between the two data, we will stick with the Qualcomm data, and whenever our Qualcomm data is insufficient to estimate a parameter properly, we will fall back to the modern standard Arabic data. And this constraint can be easily satisfied using the minimum care divergence framework. In this framework, we first select the language model, say Q-star, from the MSA text, and in the next step we have to find another language model, say P-star, from the Qualcomm, which satisfies all the constraint of the Qualcomm and is close to Q-star. Now, why do we believe this method should work? We have previous evidence that the MDI method, when applied to the switchboard, gave a 2% reduction in word error rate, and it was done in 95 workshop here. Now let me give a geometric view of the process. Let this rectangle represent the space of all language models possible, and within this rectangle, this pink trapezoid represents all the models which satisfies the MSA text marginals. Here by MSA text marginal, we mean that the model expectation of any feature equals to the empirical expectation of the feature from the MSA text. So first we have to select a point in this space such that a point in this space which is the MSA text model, language model. We can do this in several ways. Either we can use the standard n-gram process to build the language model, or use factored language modeling techniques. But in our case, we will choose the maximum entropy model. So if this point denotes the uniform distribution, our chosen model will be closest to that in minimum divergence sense. Next, consider the space denoted by the Qualcomm language model. Now, in absence of the MSA text, we can simply build a maximum divergence model, and that model will be closest to the uniform distribution with respect to minimum divergence. But since we want to use the maximum modern standard Arabic language model as a prior, we'll use the minimum divergence technique to select another language model which will be closest to this language model with respect to minimum divergence. Now let us see the parametric equations of this model. Now we know that maximum entropy model is also the maximum likelihood model among the exponential model family. So our modern standard Arabic model can be represented in this exponential form, where f and g are the factors of the model, and lambda and mu represent the corresponding weights, and z is the normalizing factor. We are We are dividing the features into two different sets, and I will explain why we have done that. Similarly, the column model can be expressed in a similar exponential form, having T and H as the features and mu as the corresponding weight. Now let me explain the features. Sorry. How do you navigate? Okay. Okay.
PowerPoint handicap.
Now let me explain the features. Here F are the features which are present only in the MSA text, and G are the features, common features present in both column and MSA text, and H represent the features which are exclusively present in the column. Now we can represent the column exponential model using a more generalized form where lambdas are 0. Now since Fi are the features present only in MSA, here for column Fi will always be equal to 0. So any set of values for lambda won't affect the likelihood of the column data. And our minimum divergence method will give us a method to select the lambda set of lambdas. And this represents the pictorial view of lambda selection. Let the big L represent all the exponential model having three features f, g and h. Within this feature, if we restrict nu to 0, we will get another subspace denoted by this ellipse where nu is 0 and has two features set f and g. So the model which maximizes the likelihood of modern standard Arabic in this will give the maximum entropy model. And let it be denoted by the blue star. So the parameters lambda star and nu star gives the maximum likelihood parameter for this modern standard Arabic model. Now let us consider another region. In this region lambda is fixed to lambda star, and we have three features f, g and nu, f, g and h. So the model which maximizes the likelihood of the column data within this region will give us the minimum divergence model. And let it be denoted by the red star. So in this model we have lambda fixed to lambda star. Instead, if we have used the maximum entropy criteria, we would have selected a model where lambda is equal to 0. Till now we have presented a generic model. Now I will focus on how to select the feature of the model and how to build the model. After building this maximum entropy model for the modern standard Arabic, I will shift to column model, minimum divergence model for column. Few notations here. I am representing the Romanized form by W, and C represents the script form of the Romanized word, S represents the stem obtained from the script form, R is the root which is obtained automatically using a stemmer, and M is the morphological tag. So a basic script form trigram language model can be denoted using this equation. And we are using this extra conditioning parameter because if a certain script form trigram is not present in the data, we can always back up to its corresponding state morphology or root. So there are 8 possible, 8 conditioning variables, so we can form 8 choose to 28 trigram templates. And for each configuration of this template, we can select the feature if it is above a certain threshold. Similarly, for the bigram case, we have 8 possible bigram templates, and we can use the similar thresholding techniques to select the feature for a model. Now the maximum entropy model can be denoted by this equation, and we already have a toolkit developed at CLSP by Junwoo to build such a model. And here F are the features which are present only in the MSA data, and G are the common features present in both column and MSA data. But since the column data is in Romanized form, we cannot directly use this script form language model. We have to somehow convert it into the Romanized form. Here we are doing that by distributing the probability mass uniformly among all the Romanized forms a particular script form can have. So we are done with this part of the modeling. Now I will tell how to develop this part for column. For column case, we have the Romanized form, so we can write a language model by this equation. In this case, we have 10 conditioning variables, so we can form 10 choose to 45 trigrams, and using the similar thresholding criteria, we can select the feature for our model. Similarly, for our bigram case, we have 10 possible bigram templates, and we can select the feature using the above method. The minimum divergence model will be given by this equation, where F are the features present in the MSA, G are the common features, and H are the features present only in column. These lambdas were calculated earlier for the modern standard Arabic data, and we use those lambda. Here, the mu will be different from that calculated for modern standard Arabic, because the empirical estimation of the parameter G for both the data will be different, and also mu will play a role in changing mu in this case. Here I briefly summarize what I plan to do. We will first start from the baseline column system already present from our workshop, and we'll, as a side experiment, we'll build a script-based language model and use the various Romanized form of a particular script-based as an alternate pronunciation, and we'll check the whole system. Next, we'll build a maximum entropy model for MSA text, and we'll do the feature selection by using thresholding techniques. So after building this model, we can build a minimum divergence model for column, and we can do something extra. If we can come up with a new learned structure, we can use that in our model. And similarly, we don't need to use the whole of MSA text. We can use only those text portion of MSA text which is similar to the column data. So in a nutshell, this is what I plan to do. Thank you.
That concludes our presentations for today, and we've already had a lot of questions during the presentations, but if there are any remaining questions, then now is the time to ask them.
Is there a language that has similar complexities in the morphology as Arabic, but has more training data?
Has no what? Training data?
Has more training data.
That's a good question. There are a lot of languages that have similar complexity in the morphology, such as Turkish or Serbo-Croatian or
Korean.
Hebrew is very similar. But I don't think they have more training data, so
Well, I
it's
think
very much the same problem in those languages.
well, if we don't restrict ourselves to conversational dialect data, there's tons and tons of text data, just as much as, on the same order of magnitude as English. There's hundreds of millions of words of text, and the same kinds of factored models can be used for text as well. Not all the same factors, because you don't have supervised training for the diacritics, but you have all the same things. So you could certainly explore the factored models on huge text corpora in Arabic or other languages.
Another answer is that I don't know whether the morphological richness of Czech compares with Arabic or not. But in Czech, for example, there is not only lots of data, but there are morphological analyzers, tree banks, pretty much any resource you can think of.
So that's mostly for formal language.
Sorry?
Mostly for formal language? Or
Well,
for conversation?
it depends on, because a lot of the text is from newspapers, but there's a lot of radio and broadcasts and that kind of stuff which have been transcribed, and some of it is kind of conversational. But I don't think Czech exhibits the kind of difference between the spoken and the written form.
Well,
like Arabic does.
even for English, I mean, it's not just other languages, right?
Right. I mean,
As we said before, English switchboard and English broadcast news are not quite as bad as this. You know, you can gain 2 points. Well, it's a little different. Basically, style is.
Why is Spanish not appropriate? Because of the fact that it doesn't have discontinuity of working?
Spanish doesn't have as much complexity as Arabic, and part of the reason for that is that it doesn't have the syntactic morphology. So it's mainly affixes versus.
It's a very simple nominal structure, but the verbal structure is pretty complex.
Right, but I think Arabic is still a little more complex. And the other difference is the amount of training data that you have for Spanish as opposed to Arabic.
I would actually, just as a general proposal, you know, my personal point of view, in trying lots of things. So we have 2, you know, different goals for different applications and all. But there's formal language and then there's informal language. And I think especially for language modeling purposes, if we can't get if we're trying a language modeling technique and we can't get it to work on formal language, then we shouldn't hope that it will work on informal language. And it's much easier to do it on formal language because there's lots of data, for example. So I would propose that as a general strategy for the community, again, this is my personal opinion, but I'm throwing it out for everybody to think about. We have to do our first explorations of language modeling techniques on formal language first to see if there's any hope for them to work. It avoids a lot of the practical problems of dealing with no data, for example.
Any other comments, questions? All right, then I'd like to say a big thank you to my team for the hard work. And I hope you all enjoyed the presentations. And thank you very much.
Thanks for the